Thank you. Thanks for inviting me to give some talks. Yeah, so I'll give 2 lectures of about 1.5 hours each, and hope to have a little break in the middle today. I probably have too much material, so we'll see how far we get. And like to so who has taken a course on quantum error correction here? Can I see a show of hands, like a master course or a PhD? So not that many. Okay, so what I'll do is I will, start pretty basic, but that means that some of you have already heard about, what are stabilizer codes, maybe a little bit bored in the beginning. And I also intend to say a few words in this tomorrow about the experimental progress and what's going on. And probably this is not something, well, maybe something you hear about. Or should I do it lower? Maybe. Is it not? I do hear I think it's maybe where my thing is attached. This, no. Christmas. This better? Sorry? Okay, good. Yeah, so I may make some references to some experimental papers that have come out on quantum error correction on the surface code, and in particular, for example, if you see here on this, this is probably too small, but this is a paper by Google that came out in July, suppressing quantum errors by scaling a surface code logical qubit, and it's the first experiment where for a really quantum code, meaning a code that can correct, both X and Z errors, they do an experiment where they take a small code, a small surface code, and also look at the logical error they get for that code, and they take a larger surface code and look at the logical error they get for that code, and they show that for the larger code, the performance is better. So adding more redundancy, adding more physical qubits gives you a better logical qubit. That's sort of the take-home messages. But of course, there are many aspects of this experiment that one can discuss, and in what sense they've shown, that things are better and what can be improved and so on. All right. Now, in terms of history, quantum error correction fault tolerance has been around for since the early days of this field, because it was very quickly realized that in order to build a quantum computer, you need something like this. You can't assume that operations, single qubit, 2-qubit gates, measurements are perfect. And you need a theory of quantum error correction like you have a theory of classical error correction. And so this was first done in terms of so-called threshold theorems using concatenated codes. And a concatenated code is something where I take, instead of 1 physical qubit, I say I have like 7 physical qubits, and those physical qubits together represent that 1 physical qubit, and represent 1 logical qubit. But then each one of those 7 physical qubits I can again replace by 7. And then I have 49, and again I can do this. And that process is called concatenation. But the thresholds for these, so these results were interesting, but more recently, the focus, in particular in relation to the experiment, has gotten onto so-called topological codes. And I bet many of you have heard about the toric and the surface code. So who has not heard about the toric code? Okay, there's still some people. Okay, so I will also cover that briefly. Okay, so let's get started. And what I want to get started by, well, let me first give you an outline of what's in the lectures. So first, want to do sort of a general introduction to qubit stabilizer codes and the notion of fault tolerance. That will take most of what we do today, but I hope also to get into aspects in part 2, aspects of surface code quantum error correction and how to do logic. And then at part 3, I hope to cover surface code decoding. So decoding is a classical algorithm. It's a classical process. And it's the following. So you're given, so you have your chip or your physical qubits, and you do certain measurements to determine what errors have happened. But these measurements do not ambiguously say, oh, the error happened there and there, and you have to correct those errors. They give you information which you have to process classically via an algorithm. And that algorithm is called a decoding algorithm. And then, you make an inference about what's the most likely error that has occurred based on the information that you've gotten. And then you say, okay, and then I correct the error, or I write down that I should keep in mind that, that error happened. Okay, so as a last topic, I want to talk a little bit about this QEC, quantum error correction realization, in particular about leakage. And for that, I'll specify I focus a little bit on superconducting qubits that you've heard about from Rami Barons. Of course, that probably just was an intro. And the reason to focus on superconducting qubits is that, well, I'm more knowledgeable about those than other kind of qubits. And secondly, besides trapped ion qubits, these are definitely the furthest advanced in terms of, being able to do error correction with. So, Google has a chip of at least 50 qubits and so on. And IBM also has some big chips. In terms of questions, I don't know how other lectures have gone with questions. Have there been many questions during the lectures or yes? Okay, so just raise your hand if you have a question. Maybe I'll pause a few times to anybody a question right now. All right. Okay. Okay, so what's a code? That's the first question you could ask. And I think the easiest way to explain what a code is, it's a subspace. So in my talk, I mostly will be talking about qubits. We have n qubits, and I can specify some two-dimensional subspace in this 2 to the n dimensional space. Now that specification, if it's an arbitrary two-dimensional subspace, not very efficient. And the good thing about qubit stabilizer codes or stabilizer code is that it's a way of very specifying the subspace in a very efficient way. Now, if the subspace is two-dimensional, I say I encode a qubit, because in this two-dimensional space, I can define two basis vectors. There we go, 0 and 1. These are just orthogonal. I just call it. And you see, I put bars on them. So this is the logical 0 and the logical 1. There's two orthogonal states. If I specify these basis vectors, I can also define a logical X. It's the operator that maps 0 onto 1 and 1 onto 0 by definition. And again, I put these overlines. This is just common notation. I also have the logical Z. And the logical Z, well, here are the relations here at the bottom. The logical Z maps plus onto minus and minus onto plus. Or you can also see it as 0 and 1 being eigenstates of the logical Z. So the specification of this space comes also with the specification of the logical X and logical Z. Now, I don't necessarily need to encode one logical qubit. There are also many stabilizer codes that encode, 2 logical qubits, 4 logical qubits, etc. So in general, for qubit stabilizer codes, the subspace can be 2 to the k dimensional, and k is the number of logical qubits that I have. All right. So now there's a few more things on this slide, but the most important thing is now I'm going to explain to you what the specification looks like. And the picture here at the bottom is the one to keep in mind. I'm going to talk about 3 groups, essentially, groups of operators. And the first group is what's called the Polygroup, denoted with Pn there at the top. And essentially, it's a group of products of polys on the n qubits. And it's not only polys, X, Y, Z, but it can also have identities in there. So it's identity tensor X, for example. And I will be using notation that, sort of mix things up. You see at the top there, yeah, so for example, if I just the tensor products of Y, X, Z, and identity, sometimes I denote it like this, but I can also denote it more like this. And maybe you've seen this in other lectures as well. All right, so that's the poly group. And, in order to make it a group, you also need some plus or minus, some phases, plus or minus I, and so on. And then to specify the code, I actually specify a abelian subgroup, and I call this subgroup S, and that's this red circle here. So the poly group is everything in blue, and S is some abelian subgroup of elements, and it has generators. And the notation I'm using is that S is generated by some elements S1, S2, and Sn minus k. So each one of these generators is a product of some polys. And these generators are linearly independent, meaning that if I take any product of these S's, I don't get another guy in this of these guys. And these S's sometimes, so these generators are sometimes called the parity checks or the chapter operators in sort of informal language. And now let me just skip one slide further. So I said we need the specification of the code space. So the specification of the code space as follows. The code space here are all n-qubit states, nu, such that for all elements in this stabilizer group, nu is a +1 eigenstate, is an eigenstate. Where's my pointer now? It's sort of frozen. Okay, yeah. Yeah, okay, there. S nu is an eigenstate of S with eigenvalue +1. So if I can describe the elements in S, and I can describe the elements in S by just giving the generators, that's an efficient description, then I can have a description of the code space. And it turns out that the dimension of this code space, I said, like, you know, it's some 2 to the k, and then I have k encoded qubits. And that directly relates to how many linearly independent generators there are in S. And basically, for every generator, so these polys, they have the property, every poly has on half of the states is eigenvalue +1, and half of the, you know, well, half of the space it has eigenvalue +1, half the space at eigenvalue -1. And so if I say it eigenvalue is a +1, I kind of reduce the dimension by a half. And I do this n-k times, and I end up with a space of dimension 2 to the k. So I started with a space of dimension 2 to the n, and I take away these constraints, end up with a space of dimension 2 to the k. This is not a fully rigorous argument, it's just to give you some idea where this comes from. Because if you actually use as codes on qubits or on continuous variable systems, the counting doesn't necessarily work out the same way. All right, so an example here. S is, I have 2 qubits, and S is generated by XX and ZZ. So X on qubit 1, X on qubit 2, Z on qubit 1, Z on qubit 2. These commute because, you know, if polys anti-commute twice, they commute. If they anti-commute an even number of times, they commute. So it's an abelian subgroup. And then I have to ask, well, what's the state that is an eigenstate of these 2 operators, XX and ZZ? And there's only one state that has this property. That's this state, the Bell state. So in this case, the space is 1-dimensional, k is 0, and I'm only encoding a state. It's not really a code or a useful code. All right, now let me go back. So I've described to you P, all of polys, and then there's a specification of S that specifies my code. And then there are other sort of special elements, and they're in another group called C of S. And C of S includes S itself, as you can see here, but there are also elements of C of S that are not in S. And how is C of S defined? Well, they're basically all polys which commute with elements in S, right? S was abelian, but doesn't mean that everything that commutes with everything in S was in S, right? I may have other operators. And it turns out that you can organize these other operators in a particular way. And so I can write C of S again as being generated by a bunch of elements. So here you see, if I can, the pointer is kind of weak. Okay, here you see C of S includes the generators of S itself, S1, S2, and minus K. But then it also includes these things, X1, Z1 to XK, ZK. And these are the logical operators of the code. And these have very special properties. And let me come to that in a moment. So these have properties that if I take X1 and Z1, they're representatives of the logical operator on qubit number 1. And these should anti-commute, as X and Z should anti-commute. But as a pair, X1, Z1 will commute with X2, Z2 and X3, Z3. right? So they present the algebra of the Pauli operators as if I just had, k normal qubits. Now, you can ask questions about this formalism. You say, well, why are these the logical operators? Well, first, it's clear that if I have that logical operators, they should map a code word onto a code word, right? A logical operator, a logical X, say, of 1 qubit should map 0 onto 1, and 0 and 1 are both in the code space, and states in the code space have eigenvalue +1 with respect to elements in S. So this implies that these logical operators actually have to commute with S. So what we need here is that S x on 0 gives me 1, and so this state again is a code word, and so we need to have this property S of that X commutes with all the stabilizer elements. One thing to keep in mind is that these things, these logical X's, or all these Paulis, they either commute or anti-commute, right? There are only two possibilities. Okay. The one other important fact is that these logical operators, they are not in S. They're not products of these check operators. Why not? Well, it's clear that if my logical operator acting on 0 would just be acting like an element in S, it would just leave 0 unchanged. So it wouldn't be mapping 0 onto 1, right? Now, one other important thing is that the logical operators are not unique. Why are they not unique? Now, of course, I can take any logical operator, logical X on 0, and I can multiply it with S. So this is an element in the stabilizer group. And this would be S on 1, but S on 1 should give me 1 again. Yeah, so I can always multiply a logical operator by a stabilizer element, and it would be a different sort of representation of the logical operator. Okay, so now let me conclude, and then I'll ask you whether you have some questions, and maybe we can just do this little. Where's an erasure? Is that what these? No. Okay, so there's one other. So the codes. This is not the right one. This. Well. Gets worse. Yeah. All right. Okay, so one more important feature of the code. So the code is specified by, okay, how many physical qubits do I start with? How many logical qubits do I get? So that's my number k. So physical qubits n, logical qubits I call k. And then the third parameter is d, is the distance. Okay, so here at the bottom, I've defined the distance. So what is the distance? In words, is the minimum weight of any logical operator. Okay, what is the weight of a logical operator? Well, a logical operator will be a string of Paulis. Let's say I have a logical operator which acts like x1 on the first qubit and y3, y3 in the third qubit, and the rest is identity. Then the weight is 2. It acts non-trivially on 2 qubits. Okay, and it should be, I can take any logical operator of the code. I can multiply it with elements in S, and I can try to minimize its weight. And that defines the distance. All right, so let's take an example for this. So there's a very simple code. It's a 4-qubit code. The stabilizer is generated by XXXX and ZZZZ, right? And so the first question is, how many qubits do I encode? And maybe I can ask your input for this. So what is K in this case? So I have 2 generators, and now maybe things went a little fast, but maybe some person that has heard about. So what's the number of logical qubits in my case? Anybody want to answer this question? So n is 4, right? 4 qubits. N minus k is 2, right? I have 2 linear independent generators. So of according to my to what I said, k should be 2. There should be 2 logical qubits. So what this means, I should be finding. Yeah. Oh, yeah. Yes. I have to erase again. Well, okay, so I'll write bigger in a moment. So I should be finding these logical operators. So we're going to find, right? So I should be, so in some sense, I say, okay, I have 2 encoded qubits. I can, there's sort of 4 basis states. And, I want to find the operations mapping onto the basis states. I'm not giving you the basis state. I'm just have to find these elements. Now, what do you know what these elements should look like? They should be commuting with the all x's and the all z's, first of all, and they should not be generated by it. So all y's is not a good choice, right? Because that's sort of the product of these x's and z's, modulo phase. And then they have to have some mutually commuting structure. But let's give it a try. So let me just write. So anybody has a candidate operator that commutes with all x's and all z's? Okay, so let's take here, these are my 4 qubits. Poly x1, does that commute x on qubit 1 and identity on the other 3 qubits? Does that commute with all x's and all z's? No, doesn't, right? What about this one? x1, x2. Does that commute? That commutes, right? Because it has an even overlap. So let me call that just my logical x1. So x1, x2. It's just a choice. It's just a name, right? What I call my first logical qubit and what's the second. All right. So what I now need to find, I need to find another operator, and I'm going to call Z1, that has the property that it just also commutes with all x and all z, and it anti-commutes with this guy. All right. I told you logical operators are not unique. So does anybody have an idea about what we could choose as Z1? Yes, C2, C3. Okay, so yeah, good again. All right. Okay, maybe I can tell you. So what if I take x2 to be well, it's just how you call things. So let me take it to be x2. So x2 logical is x2, x3. So poly x here, poly x there. Why would that be good? Again, it has weight 2, so it overlaps with all x's and all z's. And you see that, of course, it naturally commutes with x1 because it only accesses x's, both of these operators, they commute. And it overlaps with z1, z1, just like, right. This is z1. It anti-commutes twice, so it commutes. Yes, So this is the important point. And you know, if you overlap an even number of times, you commute. All right, so that's x2. And now I can take z2 sort of similarly. I can take it to be z1, z2. Or z3, z4. So I can take it to be z1, z2, and by the same argument, z2 will commute with x1. But right, so this is my, you know, this is the support of my z2. Is this clear to people? And now just the point about that they're not unique. So here z2, let's say I take it to be z1, z2. If I multiply it with a stabilizer, say I multiply it with z1, z2, z3, z4, I get, of course, z3, z4, right? Because the other things drop out. So actually another logical z2 would be z3, z4. They're equivalent. Okay, so now what is now I have identified some versions of the logical operators. And you know what I call my basis states, and depends on that definition. Now, what's the distance of the code? So anybody want to answer? So the distance is the minimum weight of any logical. If you recall, the weight is the number of qubits on which it acts non-trivially, so not like the identity. And you see here, these operators I have here, this acts on 2 qubits non-trivially, namely qubit number 2 and qubit number 3. All these others have this property that they've written down, but you can say, well, maybe I can multiply them with stabilizers so that I get even operators of minimum weight. Let's say they act only on 1 qubit. But is this possible? I don't think so, right? Because if I have a poly that acts on a single qubit, does it commute with all x's and all z's? No, it doesn't. It always anti-commutes. Right? So it can't be a logical operator. Yeah. So the distance of this code is 2. All right. So that's there we see sort of the thing in action, and you know, I've given you a fairly abstract formalism, and just by playing with examples, you get some intuition about it, perhaps. Does anybody have a question here? Yeah.
Is it obvious that you can compute the distance of a code efficiently? Because
no, it's not efficient.
Oh, it's not efficient.
No. So for surface codes, for surface codes, you can compute it efficiently. Then there are strings. So for surface code, the logical operators are closed loops, and then there is an algorithm which uses Dijkstra's algorithm that computes the distance efficiently. And we use it in a paper on hyperbolic surface codes. But in general, it's not indeed. Yeah.
So it seems like in this code, we don't actually need the 4th qubit, because like you could construct without any gates on the 4th system. But I mean, with 3 qubits, we would only
No, you do need it, because if I had x666 on 3 qubits, that would not commute with z, would it? 3 x's don't commute with 3 z's, right? But I mean, there's a 1, 2, 3, 1, 2, 3. So it means that it wouldn't generate an abelian group. Yes? Okay. All right. Now, I have not talked about all the elements in the polygroup yet. I've talked about, I've talked about in S, what's in S, what's in yellow, what's in yellow and including S is the centralizer, and about, the whole polygroup. But there are other elements out there which are sort of in the blue region. They're not in S. they're not in the centralizer. So they're sort of out here. And the feature of these elements is that they anti-commute with some elements in S, right? Because the logical operators commuted with everything in S. So gotten the logical, gotten S, gotten the logical operators. Now what's left is something that doesn't commute with something in S, right? Those are the errors, so to say. And those are the more important, they're the detectable errors. Yeah, so if I have a poly error, so look at the top here. If I have a poly error on an encoded state, E on psi, and have this bar again, denote it's some encoded state. This bar denotes it's a state in the code space. It's the eigenvalue with respect to the elements in S is +1. Then I have two options, either case 1 or case 2. And in case 1, I am in this centralizer. So, and if I'm in this sort of centralizer, I either am in S, which means that E on the state just leaves the state unchanged, yeah? Or I am in this, the centralizer somewhere, but not in S, which means that I will be some logical, right? I may be, logical x1 of the code that we just seen, or the product of logical x1 and x2. Yeah, that's bad, of course. Why is that bad? If an error happens that is a logical, I'm not able to detect it in the way that I try to detect things. Because what I actually do in error correction is I measure the eigenvalues of the stabilizers. If I'm in the code space, these eigenvalues are +1. For some errors, if some errors occur, the eigenvalues will change, they become -1. We'll see, how this happens. If a logical happens, the eigenvalues will still be +1, right? Because the logical, maps a code word on a code word, and it has eigenvalues +1. Yeah, so that's a bad thing. Now, in this case too, so that's it's sort of good in the sense that there exists an S. There exists an S in the stabilizer such that the error E anti-commutes with S. SE is -ES. And then I can use this to write this relation, namely that S on E psi, just use the anti-commutation, is -E psi. And S, I just let act on psi and it produces psi itself. So what this equation means is that, the eigenvalue of this element S is now -1. So if I measure the eigenvalue of that particular element with which E anti-commutes, I should be measuring -1. So the goal of error correction is that I measure the eigenvalues of the stabilizers of the stabilizer group, but the stabilizer group is generated. So I just measure the eigenvalues of the generators. That's sufficient. Yeah. And these are the check operators of which I measure the eigenvalues. So what that means is that if I have a stabilizer code of distance d, I can detect all poly errors of weight less than d if they're not elements in S. Why? Well, the first, the distance is defined as, the weight of the minimum weight of the logical. So if the weight is less, then it should either be an element in S or it's something that anti-commutes. And if it anti-commutes, I should be able to detect it. Yeah. All right, so now we're ready for this notation. So the 4-qubit code that we've seen with the all x's and the all z is noted like this. 4 is the number of physical qubits. The second integer is the number of encoded qubits, k, that was 2. And the distance is the third integer, which was 2 in this case. And so if we see, so this code can detect one error. Now, detecting an error is not the same as correcting an error. We'll come to that in a moment. Detecting an error just means like, oh, I know an error happened, but I'm not necessarily able to figure out which error it is, because there could be more than one error that could have taken place that could have caused this. And if I say it's that error, whereas that error happened, I may also be in a bad situation. Okay, so other codes that are popular are the Shor code. This is one of the first code. So 9 physical qubits, 1 logical qubit, 1 encoded qubit, distance 3. The Steen code, which encodes, is a little bit more efficient. I encode in 7 physical qubit. And the smallest code that encodes a logical qubit has distance 3 is the 5 qubit code. And these small codes are the codes that, of course, are of interest for the experimental implementations because the number of physical qubits that you have is rather small. All right. So now let's talk about these eigenvalues. First of all, we have to discuss.
Sorry, Barbara.
Yeah.
Over here.
Yeah.
So what do you do about those annoying errors that you can't detect?
Sorry.
The ones that are in the centralizer, but not in those.
Well, what do you do? You hope that they occur with very low probability, because if they do happen, they lead to your logical error rates, basically.
Sure, but what does that actually mean in practice in terms of the use
Well,
of error correction, right? I mean,
Well, it means that it means that the logic, if you use a code and errors happen, you will not have a qubit that has no error rate. It will not be perfect. But so some errors happen, but you hope that to be of low probability that will cause incorrectable or undetectable errors. Is that you answering your question?
well, I mean, does that mean that or is error correction then viable in practice?
So is error
correction then viable in practice to maintain my memory, or?
Yeah,
Like,
because
is
the
this a
point,
serious
okay,
problem
so
or
the
not?
point is that so maybe I should have made this more clear. So the goal is that this distance is large, meaning that if I have my n physical qubits, then d is something maybe linear in n, like n over 2 or something. That would be great, or even n for the repetition code. So then it means that logical errors would be errors that affect all the qubits of my system, and that those are unlikely to happen. Right? Sorry, that's a good clarification point. Okay. Yeah, we see codes with large distance and large k. And we can look at k over n, that ratio. And we can say, I want that to be a constant, say, like 1 over 10 or 1 over 3 even. And I can also look at d over n, and I would like that also to be a large constant, like 1 over 10, 1 over 3. And codes that have both these features, in which k over n and d over n is a constant. I mean, it's a code family, meaning I need to not just do 1 n, but I take an increasing number of n, and I have these constant lower bounds. Those codes are called good codes. I mean, I'm just making now a little excursion, because in the area of quantum error correction, was an open question for more than 10 years about whether good quantum codes would exist. So good quantum codes would be ones which have this k over n, which is the rate of the code, and d over n would be lower bounded by constant for increasing n. And classically, these codes are known to exist, and they're, well, okay, so maybe I should be more careful about these good codes. Okay, so they were known to exist, actually. Quantum good codes were known to exist. But there is a further constraint that people have been interested in, which relates to the stabilizer. So I said the stabilizer is generated by generators, which are these S1, S2, etc. And what we would like is that these generators, they could act on like n qubits, but what we like is they act on also order 1 qubit, something that doesn't grow with n. And those codes are called LDPC codes, low density parity check codes. I'm throwing this in a little bit, but because I'm not being so precise about it. Okay, so but there was an open question where good LDPC codes exist, and this has been resolved in the last few years. It's a very exciting development in quantum error correction. Okay, but those codes with high rates, k over n, and maybe large distance, are not necessarily the codes that we focus on for early experiments that are happening right now. These may come into play later in the quantum information field. All right, so now I want to talk about the syndromes And what are syndromes, basically? Okay, so I talked about that we have to measure the eigenvalues of the stabilizers. And the eigenvalues of the stabilizer are called the syndrome. That's just the way it's. And these eigenvalues, they will be plus or minus 1. So now let's say you measure a syndrome, and now you have to find what error is responsible for that syndrome. Because that would be a way of correction, right? To say, okay, no, it's that error, so that's an error that happens. But you have to be careful with what you do, because if, for example, you can observe or you can verify it for yourself that, let's say an error E happens, then I would have gotten the same syndrome if an error E prime happened, which is E times the stabilizer. Right? If the error is multiplied by stabilizer don't change the state, don't change the syndrome. So that's okay. So if I say, you know, I have to find the error E, but instead I infer the error E prime, that's not a problem. Let's say the error E happened, then I do my correction, I apply E prime. So eventually, you know, essentially I've just applied a stabilizer, which leaves the state unchanged. But more problematic is this case where, you know, I infer, instead of the error E, I infer the error E double prime, which relates to E by a logical. That's also possible because a logical does not change the syndrome. And then if I, you know, if I go on with my correction, so let's say, if I can write somewhere. What? Oh, yeah. Well, it's just a very small thing. Okay, so I have a state. My error E happens, and then I apply my correction. Let's say I apply this, and this is my correction. Then, you know, E squared is the identity. That's how polys behave. So now I got the state, which is, I've applied unknowingly the logical Z on my state. So I've changed the logical information without being realizing this. So I have to avoid this. And so this, you know, if this happens, it contributes to the error, the logical error rate. And the strategy for choosing, you know, the correction is to use what we call minimum weight decoding. So what we do is we say we have our syndrome, and then we look for the error that has minimum weight that can cause this syndrome. Yeah. And that is a good strategy. That's not always an efficient strategy, classically. It can be an NP-hard problem to decode. But for the surface code that we like, there is an efficient algorithm, which is very good, although in practice, still it's a challenging algorithm to implement, and there's much work to you know, to have, you know, most efficient implementations. Okay, so let's just take an example here of the 422 code. Okay, now I erased everything, but actually now I use this again, but that's okay. Okay, so it's clear that if an error E1 happens on this code, that you know, it anti-commutes with the all Z's, right? So the all Z's will have eigenvalue -1, but it's also clear that if the error x2 has happened, or x3 or x4, it would have gotten the same syndrome, right? So the only information I have is the syndrome, and so I say, well, maybe x2 happened, I don't know. And so then I would be applying here, you know, x1, x2 effectively, and that was just erased, that x1, x2 is a logical operator. Yeah. But one thing to note is that, okay, so the point is that this code can only, you know, if you have these two, you can only detect errors, you cannot actually correct errors. But this, of course, is true depending on knowledge that you have about the error probabilities. For example, if I know my physical setup and an error on qubit 1 was much more likely than an error on qubit 2, I would use this in my decoding and say, okay, I find non-trivial syndrome for my z's, for my 4-qubit z, and then I just choose an error on qubit 1 as the most likely event. Yeah. So the point is, what you like is you like to learn the noise and the error rates in your experiment and use that in the decoding to optimize it to choose the most likely error that has happened. And as theorists, before we do any experiment, we just assume for simplicity that these error rates are equal because we have no clue, right? But in experiment, these error rates are actually quite unequal. Okay, so yeah, so let me just now state the claim that you can, something that you can prove very simply. So the strategy of minimum weight decoding is to take the syndrome that you measure and find an error that causes that syndrome and find the minimum weight error that is. Then with that strategy, you can very simply show in one line a code of distance d is 2t plus 1 can correct any error of weight t by minimum weight decoding. And the point is that if you always choose the minimum weight error, then there's never any other error such that the product of the two would be illogical, right? Because the product, you know, the logic of the minimum weight logical is of weight d, whereas the weight of this E1 times E2, you know, can be is never of this high weight because you choose the minimum weight one. Okay, so whoa, all right. Yeah, so this is the important point. If I have a code of distance 2t plus 1, I can correct an error of weight t. So thinking back, you saw examples of codes of distance 3, which means they can correct a single error. So if a single error happens on any of those qubits and I can measure perfectly the parity checks, I can undo this error. Yeah, that's the claim that I make. Now, in practice, I don't measure these parity checks perfectly. And in practice, sometimes some, you know, not single errors, but also weight 2 errors can happen due to the circuits that I use. So things in practice are a little bit more complicated. Okay, so let's now talk about how am I doing on time? So I have until 10:30, right? Or is it, yeah. Are people okay, or do people want to ask a question? Or okay. Okay, so another important aspect of error correction is how do I measure these eigenvalues of the checks? So, for example, well, in my 4-qubit code, I had checks which were 4 x's. But I could also have a code, like a repetition code, I have a check which is ZZ. So I want to measure the eigenvalue of ZZ without measuring. Of course, I could do this by saying, okay, I measure my first qubit in the 0-1 basis, and the second qubit in the 0-1 basis. And I just XOR the outcomes, and that's my thing. But then I've measured both qubits. That's not what I want to do with error correction. I would like to measure ZZ, which is a parity, without individually measuring the qubits, because otherwise then I destroy my information. And there's a very nice circuit that does this. This is a formal, so if I have a Pauli P, this only works for Paulis because Paulis have eigenvalues plus or minus 1. If I apply this circuit here on the right, so here, the qubits here are the qubits that are in my code on which I want to measure the eigenvalue of P. And this is a helper qubit or an ancilla qubit. And this gate is a controlled Pauli. So it means that if this qubit is in state 0, I apply the identity on these other qubits. And if this qubit is in 1, I apply P. Yeah. And if you track, and so you can track the logic of the circuit by saying, imagining, say, that you come in into this circuit, say you come in with a eigenstate of, this is a state which has eigenvalue P is +1, but you can also come in with a state which is a linear combination. Say in general, I would come in with a state which is a linear combination of a state which is a +1 eigenstate of this Pauli and a state which is a -1 eigenstate of this Pauli. And then I can verify by just computing this circuit that what it does is that I do this measurement on this ancilla qubit, then it actually projects me onto either this or that scenario, and it projects me, with this probability. And in this case, I learned that the eigenvalue is +1. And in this case, I learned that the eigenvalue is -1. Okay, we're not gonna sort of do this, but if you want, you can check this for yourself. And then you say, well, okay, I have this controlled Pauli. How does this, I can break this down. For example, if this Pauli is 4 x's, so I measure this x check, then, the Pauli, you can just, this control can be spread out over sort of the control 4 times, and this x becomes the knot here. So I just have these 4 knots, and that's just represent 4 x's. And if I do this for, a Pauli being z, 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 these, instead of having these C knots, I have control Z's here. So this knot becomes a Pauli Z. You can verify yourself that this works. Okay, so that's so I need extra ancilla qubits to measure the eigenvalues, and then I can infer what errors have happened. Okay, so now I'd like to spend a little bit of time. Okay, so that's error correction, and then we can discuss, maybe tomorrow also, about what happens when, error correction is imperfect. How do you deal with this? And what's the notion of fault tolerance that I want to get to? But first, we also like to compute with the encoded information, right? It would not be useful to encode a state, and then in order to do a gate, let's say in 7 qubits using the Steen code, and then in order to do a gate, I decode it, and then I do, I have a single qubit, I do my gate and encode it again. Then, of course, during the time that I'm having my single qubits, I have the noise as usual. And the goal of error correction is to do everything at an encoded level such that the error rates at that level are lower. So typically, if my, and this is again a theorist picture, if my error rates were error probabilities for P at the physical level, if I use a code that could correct a single error, I'd like to have my logical error rates be order P squared. And P squared is less than P. And then so if I kind of, okay, but let's now talk about the universal. So what do we need to be universal? We need to have encoded versions of several gates. And there's sort of a favorite structure of how we do things, especially for the surface code. And that ties in very much with the Clifford group. Now, it's something that people are familiar with, that there's a subset of or subgroup of gates that are called the Clifford group. And people, who's not familiar with the Clifford group? Okay, that's okay. So, all right. So, and it turns out, so the gate that we need to do that's not in the Clifford group is this T gate, which looks like a very innocuous gate. It's just some rotation around the Z-axis. Here's the definition, but it's not in the Clifford group. And it turns out to be a lot more hassle to do this gate. And we know, of course, that if we have a circuit that only uses Clifford gates, then we can classically simulate it. And actually, the error correction circuits that I just showed with my parity checks also only use Clifford gates. So if we're at a stage of quantum computation where we only do encoded logics with realizing Clifford gates, we can simulate the whole thing in principle. We're not doing anything non-trivially computationally. Okay, so what I want to show in these lectures is some ways to do the C0 and some other of these gates in the surface code. Okay, so now one thing about, this is about fault tolerance and encoded logic. This is a full slide, so let's not look at all. So Okay, so there are some ways of doing gates which are very simple. So let's talk about that first. And those ways of doing logical gates are called transversal. And an example is here. So for example, I have to do a C0, and I've encoded my qubits into a block. So I now have two blocks, and I have to do a logical C0 between the logical qubit here and the logical qubit there. And each logical qubit consists, say, of basically seven qubits. And now, a very nice way, if I can, if it works, is that I would do a C0 between the first qubit here and the first qubit there, and then the second qubit here and the second qubit there, and I can all do them in parallel because, they act, they act on different qubits. So that's sort of denoted here. And that is a way of doing a transversal C0. And now it turns out that many codes have a transversal C0. So the surface code has that. CSS codes have this generally. It's a subclass of qubit stabilizer codes. And what is so nice about the transversal C0? Well, it's very low depth, right? I can just do everything in parallel. It takes one step. But also, if I have an error on, it's the spread of errors that is important. If I have an error on one data qubit, okay, so maybe on this first block, I have an error on the first qubit, it can spread to the first qubit on the other block because it's acting, there's a C0 between those, but it won't spread to other qubits in the same block because I'm not doing any other gates in the same block. And that's important. For example, if I have my 7-qubit code that corrects a single error, if I had a single error that could become 2 errors in the same block, and I can't correct 2 errors, then it means that a single error could lead to 2 errors I can't correct. And so have I made anything better than with error correction? Probably not, because there's many ways in which single qubit errors can happen. If they're all spread to 2-qubit errors I can't correct, this is terrible. So it's, it's highly non-trivial that adding redundancy for error correction actually does work, because I'm adding many more places in which errors can happen. So only by being very careful about how I can error spread and detect can I actually sort of, handle this. Okay, so one thing, so for example, here is another sort of transversal case. Now there are other sort of generalizations of transversal cases. Where's my cursor again? So this is a Hadamard gate. Now where is the? Okay. Oh, that's up there. Yeah, sorry. Here's a Hadamard gate. Now for the
sorry,
yeah,
I'm problemistic. So what is exactly the definition of transversal? So is this the thing that you can do in depth 1 or what?
Okay, so yeah, it's a good question. What's the definition of transversal? Because it's yeah, let's say it's depth 1, and you can so you can really do it via let's say I have to do the single qubit gate here, then I could do it as single qubit gates on every qubit in the block, and it doesn't need to be say all Hadamards. If I have to do a logical Hadamard, for example, there are transversal constructions for an S gate which use S and S dagger, right? But if it's in some sense it's nicer. There are also ways in which you generalize transversal to being constant depths, and constant depths, then an error can spread to order 1 block, and that for some if your code distance is more than at order 1, it's also good. Okay, so but the point is, it's often more like people discuss about the specific constructions you have to do gates, and don't emphasize the definition of transversality that much, because you can also sort of like say I permute some qubits, and is permutes do something that it acts only on pairs of qubits in 2 blocks, and then I also permute some qubits, and that's also allowed. That's also kind of transversal. Right? So there's some room for these things. Okay, so sorry, there's something that I missed there. Now, a very important property of the Steen code and generalizations thereof is that all Clifford gates are transversal. And so there is a circuit for this Hadamard that looks like this, but there's also a transversal circuit for the S gate. And the Steen code is the smallest 2D color code. But there's also, so 2D color codes have been extensively studied and compared with the surface code. But the problem is that even the Steen code, so what the Steen code is the code where I have at these numbers that you may not see, they're qubits, so there's 7 qubits. And every one of those, so these faces like red, blue, or green, they correspond to both X and Z checks. So for example, the blue face acting on qubit 2, 3, 5, 6, there will be, an X2, X3, X5, X6 element in the stabilizer and a Z2, Z3, Z5, Z6 element in the stabilizer. But the generalizations of this code, it's actually happening on a hexagonal lattice. There are other variants also on a square octagon lattice. But the point is that if you have this hexagonal lattice, then the checks will act on 6 qubits, because it's a hexagon. And you have an X check for every hexagonal face and both a Z check. And that looks very innocuous from a theory point of view. But to measure an X check of weight 6 is more complicated, requires more C0 gates, if you've just seen. It requires 4 C0 gates than an X check of weight 4, as you do for the surface code. So there's a sort of currently surface codes are experimentally more attractive than the color codes, but the color codes have an intrinsic advantage, which is that the S gate is transversal, which is not the case for surface code, and we'll come to this later. Now, one more thing I want to say about how to do encoded logic, and it's an important point, is that it's not that hard necessarily to come up with ways to do, say, a T gate in a non-transversal manner or in some other manner. For example, for the Steen code, this circuit here on the right is doing a logical T gate via some 2-qubit gates. Here, it's this one. But the problem with this circuit is what I mentioned before. Let's say a Z error, I don't know if you can see here, a Z error occurs here. And what happens is that you can say, well, how does this Z error spread? What does it become? And so it turns out that if you put in a Z to this C0, it spreads to the control, and then again, it spreads here. And the effect is that actually this Z error this circuit is equivalent to having done the logical T, and then after that, having done a logical Z operator. So that Z error has directly led to a logical operator. So that's very bad, right? That's not what we call fault tolerant. So this is important because some people think like, okay, I can't do the logical T, for my surface code. Well, the point is you can't do a logical T fault tolerantly. You can't do it in a way that it bounds the error spread in a way that we can correct the errors, and that actually using the code has any chance of giving better performance than using no code. All right. So, okay, so now maybe I want to say a few more things about fault tolerance. So getting fault tolerant constructions of gates and also of quantum error correction is an important area, and there are many constructions that are known. And it can be sometimes a bit confusing if people ask, what is fault tolerant? I've had this question many times from experimentalists. And I'm not sure I have a good answer to it. I think sometimes fault tolerance, well, if the circuit is that you use a fault tolerant, there's a chance that your logical performance is better than your sort of, basic performance without using the code. And it gives you a possibility. And let me maybe explain this. And the way we're going to look at this is the following. Is look at the very simple sort of experiment or setup. Let's say I had a qubit, not responding. So here I have a qubit in a qubit I've prepared in 0. I do some single qubit gate U, and then I measure it in the Z basis. Those are 3 steps. And every step can fail. So every step with probability 1 minus p, the thing happens perfectly. I prepare my 0, and with probability p, something else happens I have no control over. It's just the garbage. I mean, I'm just, maybe completely mixed things gets prepared. And so clearly the probability that the sequence of 3 steps fail is like this. So, 3 places of an error, so 3 times p, and then the other places don't have an error, so that's 1 minus p, so 3p times 1 minus p squared. So that's like order 3p, and so of course I've had a sequence of n steps, it would be like n times p, roughly. And now the goal, and of course that if n is large enough, and p is just given, I can't change it, then at the end of the circuit, I get garbage. This is the problem of quantum computing, right? Too many gates after each other, you get garbage at the end. Now, what we want to do with fault tolerance, we want to replace every step, and these steps are also called locations, but maybe I'm still the only one who uses this notation, this sort of terminology. So prepare a 0 is a location in the circuit. Doing a unitary is a location in the circuit, and a location can fail. A qubit idling for some time is a location in the circuit because it's idling because there's some other gates happening, and I can't change these gates. But so I replace these locations, and I would like to. So in my native model, every location fails with some probability p, and I want to replace it by sort of a unit that fails with only probability p squared. Because then, I've made life better. And especially when I use the bigger codes, then I can deal with an n, the depth of the circuit, which can get very long. And the point is, if I have a unit that replaced p by p squared, and now the next replication of this would replace p squared by p to the 4th, it goes, like p to the d to the r, where r is sort of a recursion level. Okay, so the replacement of the unit is that I replace my preparation of 0 by the preparation of a logical 0, and I follow it by some unit which I called QEC, quantum error correction. I haven't yet specified what is happening in this unit. I'm going to specify what properties these units need to obey, the sort of fault tolerant design principle. And then I can say, can I make this for a certain part? And again, the logical, the U will be replaced by the logical version of the U, and again, some QEC unit. And the measurement in the Z basis will be replaced by a logical measurement in the Z basis. It's a description of what I need to do on the device, to do this measurement. And the goal is, so the goal is that this whole sequence now will have an error probability which scales like 3 times p squared. And the similar notes that there is still some prefactor that I've ignored here, but the 3 relates to there be 3 units, and so with n steps it should be something like n times p squared. But again, there's a prefactor, and when this prefactor is very large, then prefactor times p squared may still be larger than p, in which case my error correction is bad, it's not useful yet. But if p is low enough, then my constant times p squared will be less than p, and so my error correction will be effective. All right. Now we want to understand a little bit how can I get this scaling of p squared? What do I need to obey? Now, one property I need to obey. Now here I've put in some errors. Say these red stars are errors, and sometimes these errors are called faults because they're sort of like the basic things that happen. And one thing I have to keep in mind also, that if I do some 2-qubit gate, I should assume that there could be, a 2-qubit error after it with some probability p. Like, I only have one parameter p, which, sort of says that's the total, that's the only parameter in my noise model, which is very simple, of course. But the point is, if I do a 2-qubit gate, I shouldn't say, well, the probability that there are one error there and an error there is order p squared. That is often, why should I not do this? Because it's not experimentally warranted. You can't assume that if you do a 2-qubit gate, you avoid 2-qubit errors or they're lower, one sort of order lower error probability. Because you're entangling these things, you are creating correlations. Okay, so these faults can represent 2-qubit errors in the circuit. And I have to look at what happens with them. For example, I am doing a QEC unit and say a fault happens in this. And that's my fault here. And here I've drawn a circuit. Let's say this QEC unit has a fault that is an X error here in the middle. And I can ask myself, so it's only this one here on the ancilla qubit. And what happens with that error? What is its effect when I execute the circuit? And you see, because you flip this ancilla qubit, it actually propagates 2 X errors on the data qubits here. But let's say I'm using a code that corrects a single error. And now what I've seen is a single error here in the middle causes 2 errors. So wait, does it mean that if those 2 errors then propagate, let's say they propagate through this, and this is transversal, so they just pass through, and let's say now they hit the QEC, there's no more error, then maybe I can't even correct this, right? So I have to be very careful, especially for codes that correct few errors, that this error, even though it's weight 2, it is still correctable. This is not a priori at all obvious. And for example, for Steen code, you need extra ancillas, you need extra flags and stuff to ensure full tolerance. For the surface code, this type of error, by ordering the C-naughts in a certain way, you can avoid that this 2-qubit error cannot be corrected. So certain 2-qubit errors you can actually correct and others you cannot. So you have to be careful about this. Okay, so that's one thing about that the QEC unit should not, like, if a single error occurs in it, it should lead on output to sort of, having done the QEC error correction, and then maybe there's a 1 or 2, there is a correctable error on top. There's maybe a correctable leftover error, but there shouldn't be an incorrectable leftover error. Now, there's another issue that you have to be careful about, because if you place errors in this way, let's say you can say, well, if I have these errors happen in this first QEC unit, in the middle, and in the last, can I correct for this in the sense that the output of this logical Z at the end gives me the correct answer, exactly the same answer that I would have gotten if I were to perfectly run this original circuit. And this can also be troublesome because an error in the gate U and a fault in the QEC can lead to 2 errors in total. So I can have sort of, this error and that error, and then they come into there. So there is an issue. So you have to be careful, especially for low distance code. And actually, for codes that are low distance, you want the following property. You're trained to strive for this. Now, in this circuit, you have to just note it's a bit complicated. So what I've done is I've made rectangles. So the rectangle is something that I take the operation and I pend it with a QEC unit before and after. So for example, here's my operation KU, and I pend it with the QEC and the QEC after, and that I sort of, put a big box around it. And that's, in some technical language, it's called a rectangle or an extended rectangle. And if I do a preparation, I can't extend this rectangle further back, so it's just preparation QEC. And here in this thing, I've inserted another identity gate. It just I've run a slightly longer circuit, but you can do this for a very long circuit, say on a single qubit. You make these boxes. Now, the point is this: the claim is that, or the goal is this: if there is at most 1 fault in each extended rectangle, 1 fault in a rectangle, so that means that I have to spread out the faults sufficiently, and all units are fault tolerant, which I haven't defined yet, but I'll give you pictures in a moment, then the entire sequence of rectangles will have no overall error. That's the claim. So it means that if I have a fault here, you say it's happening here, then it leads, because this QEC unit is fault tolerant, it leads to at most 1 correctable error on output, goes into the gate, the gate won't spread the error to an incorrectable error. That is the property of fault tolerance of the gate. Then this QEC unit here will be faultless because the fault occurred here, and it will correct the error, right? And similarly, for example, here, if I, and then again, could insert another error here with my QEC thing, and maybe this QEC error feeds into, it leaves a leftover error that feeds into the logical Z measurement, which also includes some error correction that will correct the error. So the point is that these events will lead to no error. So I need to have at least 2 errors in extended rectangle or 2 faults in extended rectangle to get a logical error, to get failure. So then it's a matter of counting how many ways are there to put 2 errors in extended rectangle, at least. And that, of course, to have 2 errors, like if one error, one fault has probability P, 2 errors have probability P squared, and then I have to look at the number of ways to put these errors down that lead to incorrectable errors. But it will scale like P squared, right? So this is the argument that if the units are fault tolerant, which I haven't properly defined, that my logical error rate will scale like P squared. Yeah, and then with n steps, it will scale like n times P squared, because they say, okay, so failure occurs when one of these extended rectangles fails. Okay, 1 out of these n, and then in order to fail, it needs the P squared, it needs 2 faults. All right, and now what is the fault tolerance in pictures? So what is it in pictures? It says, okay, so what does this say? Here I have the QEC unit, and incoming in it is a single error, and the QEC unit has no error, then it should correct the error. So the output state is just the state. Okay, so similar, here I have a single error and the state. I get it into the logical gate. Then on the output, I should have done the right logic, so use applied, plus a single error. This is only, full tolerance for a distance 3 code that can correct a single error. Now here is a picture where I say, okay, I have a perfect state, some code state comes in, QEC unit has 1 error, then I should have a single error on output. But there's a little caveat, really I should just have a correctable error. Okay, that's the condition, because sometimes I can't actually get full tolerant circuits that have this property, so I have to relax it a little bit. Okay, so again, if the gate has a unitary, I have to have a correctable error plus the right logic. Now here there's some other technical conditions. If I have some unknown state, I'm not necessarily code space, and I'm doing QEC unit, now you don't see what's going to be the output, then you have to have some encoded state. And again, if I have an unencoded state and I have a QEC unit with an error, then I have to have some encoded state. I don't specify which one it is because my incoming state is kind of like completely messed up, plus a single qubit error. And here I have a single thing, so with preparation, if I have a single fault in here, then it should at least at most 1 correctable error on output. And similar here, if I have a faulty state coming in and I do a perfect measurement, I should get the right outcome because the measurement has to have some native error correction in it. And here, if I have a perfect state coming in, but the measurement is actually incorrect, again, a single fault only, then I should infer the right outcome. So that's in pictures, the sort of conditions for fault tolerant design that you have to obey them. All right. Now, the fact is that if you read papers on fault tolerance, it's not necessarily they check this. Checking these things is actually kind of tedious. And sometimes it's like, sort of a complicated proof somewhere that says, oh, this circuit's fault tolerant. It's not so simple to test. And I struggled a little bit whether we should have sort of more, more routines because you can sort of, what you could do is you say, I run a Clifford simulation, I insert all possible faults, and I just see what happens. And doing this numerical, is more efficient than kind of arguing by hand, like if the fault happens there, this happens, and then that happens, and then I can correct it. And then you have to go through many, many cases. And I think sometimes it also leads, it's a these are subtle properties, this tracking of single errors and what they, what their effect is. Yeah.
Question.
Yeah.
So do these pictures like with a single error that stays single error, does this also apply to like, would this be your definition of fault tolerance for any distance code or just for this small code?
No, just for the small distance code, but there are versions of these pictures in Alafer's, Gottesman and Preskill paper that apply for any code. So they're more general indeed. Yeah. But the point is more than you can also phrase things in terms of yeah, for example, if you have a distance D code, it can correct T errors. So if T faults happen in the unit, they shouldn't lead to an incorrectable errors at the output. But the problem is this okay, so the problem is this. So for the surface code, which is very commonly used, the distance is something, but the code can actually correct many more errors above the distance. So then you say, well, if I ask, you know, so I have to actually talk about the errors that it can actually correct instead of like relate things to the distance. But you can still say, well, okay, so I can ask about, you know, T errors and that should the code at least correct, but then there may be other errors that the code can correct as well. So this formalism is not so used very well, but still for small codes, I think it is useful to sometimes break down what is actually happening in terms of these units to understand the fault tolerance or the fault tolerant design. Other questions? All right. So now let's start with, so now I want to switch. So after this sort of broad intro, which I hopefully was useful, I want to talk about aspects of surface code error correction, logic and decoding. And the surface code has become the favorite sort of near-term or implementation for error correction. And there are several reasons for this. First of all, is that the circuits that you use to measure the parity checks, you know, you need ancilla qubits. You need to place these ancilla qubits somewhere near your data qubits, or at least you need to do C0 gates and control Z gates. And this can all be done in a two-dimensional plane for the surface code. Maybe you've heard Rami Barnes also talk about this. So this two-dimensionality is appealing. A second appealing feature is the fact that the parity checks, the generators of the stabilizer group, are weight 4 or weight 2 at the boundaries. They can be weight 2 or weight 3 even. And in the bulk, they're weight 4. And so that's fairly low. There are there's a subsystem version code of the surface code that uses weight 3 parity checks, but it has other disadvantages, has a lower threshold and so on. So those are, and then the decoding is relatively simple and well understood and efficient. So those I would, but then there is a list of disadvantages like the non-transversal S gate, and the fact also that the rate of this code is sort of, you know, quite poor. But rate is not something that we're concerned with sort of in the very near term. If people complain about overhead for error correction, right? Because every physical qubit you have to replace maybe by a block of, say, 13 qubits or even more. And this generates a huge overhead. And people have looked theoretically at constructions where you have much lower overheads. But I think, again, these are not like near-term practical. You can ask me more questions about this. Okay, so there actually are several incarnations of the surface code. There's the what's called the rotated surface code. There's the Tor code, and then there's sort of the straight up surface code. And so this is the first version that's sort of now a little bit less popular, where the smallest version is a 1313. And you see 13 is quite large compared to the other codes you've seen, which encode a single qubit and can correct one error. So it's not so efficient, and that's why other versions are more attractive. And here you see the generators of the check, the stabilizer, the plaquette, and the star operators, and also the representative, the logical Z and the logical X. And the but let's just yeah. And so if you take that lattice and you put periodic boundary conditions in both directions, you get a torus, and then you get the toric code, and that actually encodes two logical qubits. And here you see the logical operators that have mentioned them for this other code. So they xz1 commutes with x1 because they overlap on a single qubit, but they mutually commute. And you see that the point is of the toric code is that these logical operators, they go around the whole lattice. So the point is, if you say, well, it has to commute with the stabilizer, you have to make these loops around the two non-trivial loops of the lattice. And therefore, the length of these loops, they're called the systoles, also, they set the distance. So you have a very natural lower bound on the distance. It's easy to determine. And you can actually generalize. We studied surface codes. You can, like here you see a multi-handle torus, and then if you have G handles, you can encode 2G qubits. So per handle, there's sort of 2 qubits. And then you can tile this torus with these square tiles. And then your rate and all these and thing, this would be similar. It would not be very different from having this sort of separate, tori. But you can also take a different tiling that we've looked at. And for example, if you were to glue, so here, you have 4 squares and they attach at one vertex, right? But if you were to take pieces of paper and you have a little square, and you try to attach 4 of these pieces of paper, these squares if you try to attach 5 of these squares at one vertex, you'll find that this paper will start to, crumple. You can't do it. You can't fit this in. And this notation here, let's see. So there are so-called hyperbolic surface codes, and this notation shows, I have squares, so 4 sides, and I put 5 of them at a vertex. So the toric code would be 4, 4, and 4, 5 is a tiling where I put 5 squares at a vertex, and that generates a hyperbolic tiling, like the thing's gonna curve, right? I can't make it in the Euclidean plane. And those have encoding rates which are much better. We studied some of those. And the toric code can also be generalized to higher dimensional codes. But then again, you have these problems with experimental realizations that are not necessarily in 3D. Okay, wait a moment. Why is this not? This not work? Oh yeah. Yeah, okay. So the favorite surface code that is looked at now is what is sometimes called the rotated surface code. So on these other surface codes, the qubits were on the edges. In this model, in the pictures I've shown later, the qubits are on the vertices. And so the smallest guy that you have is this code where I have 9 data qubits on these 9 vertices. And these squares, white is a Z check acting on those 4 qubits, and black is an X check acting on the 4 qubits. And these half things are weight 2 checks on the boundaries. And so I can make a small guy and I can make a bigger guy. And so if we refer to this experiment by Google, they have essentially realized this code, which has distance 3, because the logical operators go, you see the logical operators go along these edges of this lattice. So they touch on 3 qubits for this small thing. And they've done the next bigger up version, the D is 5. Actually, they haven't quite done this version because they have done some Hadamars on these qubits so that the checks are not all X's and all Z's, but they're mixed, but that's a separate point. Okay, so I think we should stop here then. All right. Yeah, of course I could continue, but I think time for questions is good, I think.
Thanks very much. I think we should take the time, another couple of minutes for questions, and then we just start a couple of minutes later, the next one. Anyone like to follow up?
I wanted to ask like how damaging a syndrome measurement is. So apparently in current hardware, like error rates for measurements are much worse than for gates. And for one syndrome measurement, you need to measure n minus k different stabilizers. So how damaging is that?
Yeah, I wouldn't say the measurement is the problem. See, okay, so the problem is indeed for the syndrome measurement, you need to execute these parity check circuits, like, you know, all over the code lattice, and every data qubit participates in 4 of these checks. So there's sort of, it has to do a C naught between, and these C naughts or control Z's are a source of errors. You know, the 2 qubit gates are worse in fidelity or in error rate than the single qubit gates. So the fact that the measurement, let's say if you have interacted your ancilla qubits with the data qubits, and then you are separately measuring the ancilla qubit and then it's faulty, that does not necessarily impact the data qubits, except of course that if it leads you to infer incorrectly what the error is, right? But for that, so so if you do, you can ask the same question for the repetition code. So one line, you know, so just a classical code. And you can ask, what if I vary the probability for error for my, how sensitive the threshold to my measurement error for my ancilla? And it turns out to be quite insensitive. And that's because if you do enough repetitions of this parity check, you will pick up when, you know, okay, this syndrome is just wrong because it flipped one time and it's sort of flipped again afterwards. And then it's, so you pick up, you learn information about unreliable syndrome, should I say. So my answer is the more damaging is the fact that you have to interact with the data qubits and the errors that introduces on the data qubits, like this thing that I showed, like an X error on the ancilla feedback, rather than the measurement of the ancilla qubits. Because in theoretical models, like for the surface code, for this, the repetition code is very simple. If you look at the threshold plot, you can actually get a very high error rate on the measurement of the ancilla and still be below threshold. I mean, it's sort of like, you have to have low incoming error rate as well, but you can, it's pretty lenient, so to say.
So the stabilizer formalism is made for correcting against Pauli errors, right? What happens if you want to correct against a larger error class? Let's say C naughts can happen. Is there anything similar as the stabilizer formalism?
Yeah, it's a very good question. And I completely should have not mentioned this, that it is a fundamental sort of you know, factor, property of quantum error correction codes that have been derived early on, that if a code can correct Pauli errors, it can also correct linear combinations of Pauli errors. And so, for example, if I say I do a C naught gate, then I can expand the C naught gate, noisy C naught gate, as something where I do, say, a perfect C naught gate followed by some channel. And this channel has Krauss operators. I don't know, I assume that this, and these Krauss operators can be viewed as linear combination of like identity plus, you know, Pauli's, you know, the linear combination of X identity, XY, et cetera, right? Because the Pauli's are a basis of the matrices that act on 2 qubits. So the point is that but the only subtlety, so you can, yeah, so if like I put in some single qubit error, I say there's an X error here, but I could also, the point is if I put in a linear combination of X, Y, and Z errors, I can also correct it. And what you see also, for example, like when I was discussing what the parity check does, you know, for example, if a rotation error happens, let's say I have a Z rotation on a qubit, and it partially maps me to a superposition of being in the code space, so having +1 eigenvalues, and having -1 eigenvalue for some stabilizer. So I'm in this superposition, you know, with some coefficients alpha and beta, and it's like it's a slight over rotation, so alpha is a lot larger than beta, right? So I have just a linear combination, and then what my parity check does, if the parity check is perfect, it actually projects me onto having no error with probability alpha squared, and having the error with, so it basically what happens is if I have linear combinations of errors, or coherent errors are often called, over rotations or other things, then my parity checks project me onto Pauli errors with probabilities that correspond to the amplitudes with which the errors came in. But this is, of course, the parity checks if they're perfect, but in practice, they're not perfect. So this doesn't happen completely. And the other thing is that people have studied it a little bit, say, well, what's the probability for error then? If I have a coherent error, if I have some Krauss map that maps has, if I have some channel that has Krauss operators, which are linear combinations, what's my error probability? How do I extract this? And is that probability relevant for assessing logical performance? So people have looked at those questions. Does that answer your question? Yeah. Okay. Yeah, and of course, this is all about qubit errors, right? There's also other errors that come through that are leakage, they go outside, and that's different. Yeah. Yeah.
Yeah, there's one from the chat. Is there ever entanglement between the physical qubits in one particular block, or is that
Yes.
something to be avoided?
No, it's very important that there is entanglement. So so we never, in stabilizer codes, we don't typically write out the code words, but they're highly entangled code words. And you can also see this that, let's say, if you look at the logical 0 and the logical 1, and if you just look at the reduced density matrix on one qubit, they would look identical. And this is for a reason, because if, say, a little daemon in the environment could say, okay, I'm going to measure the single qubit, this single qubit, I'm only going to touch that single qubit, and I'm going to figure out whether I have a logical 0 or 1, then I've destroyed my information, right? There's no way I could undo this action by this daemon. So the local reduced density matrices should not reveal whether I have a 0 or 1. So I have skipped quantum error correction conditions, and these also capture this. So if you want to read on this, Nielsen Schwang also discusses this.